So now moving into inverses and what those look like in a matrix context, I want to help you understand that really well and compare it with real numbers. So kind of over here, I'll give some examples using just numbers, and then we'll kind of move ourselves over into the matrix realm in terms of inverses. So it depends on the operation that you're using. So we're going to compare adding versus subtracting, and then the same, or not subtracting, multiplying, and then adding versus multiplying in both realms. So if we're trying to illustrate the inverse property right now, just the inverse property, when we are adding with real numbers, so if I have like 1/3, then when you do 1/3 plus negative 1/3, you're going to equal 0. And so what you get right there is you get what we consider to be the additive identity as your answer when they cancel out. However, when you multiply, if I were to take, let's say, negative 1/3, then I would want to multiply it with its reciprocal, which is -3, which gives me +1 as an answer. And that right there is what we consider to be the multiplicative identity when we're talking about real numbers. Okay, so that's our two examples of inverse property with real numbers, one with addition and one with multiplication. So with matrices now, the addition version is very easy to understand based on what we've covered so far. So if you started with a matrix that had -2, 5, 1, 0, and you wanted to demonstrate the inverse property with adding, they just need to equal the 0 matrix at the end. So then the matrix you add with it, of course, just has to be the opposites. So 2, -5, -1, and 0. And so what we do get right there is we do get an identity matrix, and that's what we consider to be the additive identity matrix, is the 0 matrix, right? We give it a capital O sort of letter. So what that then means is if we're doing multiplication, right, don't we want this matrix that we get right here to be the multiplicative identity matrix, right? And the multiplicative identity matrix we resemble or we represent with the capital letter I, which means it's going to have 1s in the main diagonal and 0s everywhere else, right? So if we're given some sort of a random whatever matrix to begin with, then we want to know what we multiply it with, right? So that these are going to be multiplicative inverses of each other. Then how do we go about determining that? And that's territory we haven't gotten into yet, but it's territory that we're going to get into right now. So if we assume that this first matrix right here has elements A, B, C, D, okay, then what this matrix needs to be right here, I'm going to define for us right now. So here's your A, B, C, D matrix, right? The inverse of it, so the matrix you would need to multiply with this given matrix, would have to be the following. So the inverse of the matrix is as follows. So we give that little -1 that's a superscript right there, that's the symbol that we use for the inverse of the matrix. So I want to make really clear up front right here that that -1 is not an exponent. I'll say it again, it's not an exponent. It's just symbols that we use. It actually makes a lot of sense why it's a -1, but that's stuff that we haven't gotten to yet and that we'll get to in the future, and you'll understand why we kind of use a -1 a lot in superscript lettering there to represent an inverse. So the way you'll want to read that is read this as A inverse. And to find the inverse of a 2x2 matrix, the way that you will do so is to do the following. You will take 1 divided by, so I put the bars around the A, which means the determinant of A, and then you will multiply it by a matrix where you will do the following. So the elements D and A, so the elements in the main diagonal, they swap positions with each other. So you can see that. But the B and the C elements stay where they are. However, both of them become their opposites. So you make them negatives of one another. So whatever that simplifies out to be will be the inverse matrix that you need. That would basically kind of go right there, so that then when you multiply these two matrices, they'll cancel each other out, and give you what the multiplicative identity matrix is going to be. Okay, all right, a lot of stuff right there. So let's go through some examples so that we really can comprehend what it is I just kind of introduced right there. So read what it says. It says to determine the inverse matrix of each of the following, if possible. So we're just trying to find the inverse matrix of W. So to find the inverse matrix, okay, we read that as W inverse, don't say to the -1 power, it's not an exponent, W inverse, okay, it's going to be 1 over the determinant of W, so we're going to come back for that number right there, and then you're going to multiply whatever that fraction is going to come out to be with this matrix. So I switch the numbers in the main diagonal there, and then the other numbers stay where they are, but they become their opposites, like you see there. Okay, so we just need to find what that number is supposed to be in the denominator right there, and that's supposed to be the determinant of W. So to find the determinant of W, you have to take the product of the main diagonal and then subtract away the product of the other diagonal. So I have to do 27 times 3, which is 81, and then I do 4 times 21, which is 84, and then we subtract, and we end up getting -3. So that -3 becomes the denominator there. So it's really just you have a fraction -1/3 in front of a matrix. You just times it, right? Times it with all the numbers inside. So we end up getting -1/3 of 3 is -1, and then we get a positive, because we're doing negative times a negative, so 4/3, another positive 7, and then -9. So this right here is what was asked of us, because it just asked to determine the inverse matrix of W here. So what this means in terms of application is that's the matrix that when we multiply it with W, it's going to equal the identity matrix. So really fleshing this out, if you were to take 27, 4, 21, 3, and then multiply it with the matrix -1, 4/3, 7, -9, it will equal the identity matrix like that. So you can take the time if you would like to go through the pairwise multiplication, that sort of process. It does end up working okay and is valid in that regard. So yeah, in terms of finding an inverse matrix, just kind of using that same sort of process for a 2x2 matrix, x inverse is going to be always the number 1 in the numerator there over the determinant of x. So let's go ahead and find that determinant right away. How about now? So the determinant of x will be the product of the main diagonal, which is -21, and then the product of the other diagonal is -18, but we subtract -18 away. So we're actually going to end up adding right there. So actually, yeah, we end up getting -3 there again. And then the matrix right there, you swap the positions of the numbers in the main diagonal, and then the other ones become their opposite. So since that was a negative, it becomes positive, but then that was positive, so now it becomes a negative, and then just multiply everything by -1/3. So that turns out to give you x inverse is going to be -1, -3, +2/3, and +7/3. So that's the matrix that you need to multiply with x there. So kind of one interesting thing about matrices in trying to find an inverse is sometimes you won't be able to find an inverse for a particular matrix. You'll kind of run into a problem with that. And so I want to exemplify that. I'm skipping a little bit of stuff that I'll come back to in a little bit. I want to exemplify that with this right here with matrix H. So it says to find the inverse of the matrix. So in other words, find H inverse, because that would be the inverse. So we'd have to do 1 over the determinant, and then we'll swap those, make those negative, but stay in the same spots. And then we need to find the determinant, so that would be 15 times 6 is 90, and 10 times 9 is 90, and 90 minus 90 is 0. That right there is a problem, because dividing by 0 is undefined. So that right there is not even a number, right? It's undefined, which then means that ultimately we're not actually able to find H inverse here at all. So what that means is that H inverse does not actually exist. There is no multiplicative inverse of the matrix H. And so the only time that will actually ever happen is when you get a 0 right there on the bottom. And since that's actually the determinant of H, you don't have an inverse for a matrix when its determinant is 0. So just kind of going backwards here, there was some kind of space up here that I left blank that says that if you have the determinant of the matrix A is 0, then its inverse actually does not exist at all. So yeah, you won't be able to find an inverse. So whenever that happens, then we would call a singular matrix when it doesn't have an inverse. So it's always a singular matrix when the determinant of it is 0, and then that leads into the fact that it doesn't have an inverse. So yeah, so we kind of broke apart things with real numbers earlier and then with matrices earlier. So in terms of real numbers, does every real number have an additive inverse? And so when you think about inversing with adding, right, can you always add two numbers, cancel them out, and equal 0? And the answer to that is yes, right? You can always take like negative pi and add positive pi to it, and it'll equal 0. So that's always going to hold. Does every real number have a multiplicative inverse? So that means that you're going to multiply and equal 1. So are there always two numbers for that? Kind of, almost. And what I mean by that is, like, you can do 1/2 times 2 and multiply those reciprocals, and that'll work out great. You can also do like 3/4 times 4/3, and that'll work out great. The only time where it doesn't work out is when you have a 0. Because then if you reciprocate a 0, you're going to have whatever number there and then a 0 on the bottom, but the problem is that doesn't exist. So the only number that doesn't have a multiplicative inverse is just the number 0. So almost, so to really answer it like definitively, does every real number have a multiplicative inverse? Then like no, right? In terms of additive inverses for matrices, is there a matrix that you can add with a matrix to equal the 0 matrix, right? A bunch of zeros. And the answer to that is yes. You always can find opposites for numbers. But in terms of multiplicative inverses for matrices, the answer to that is no, because if the determinant of the matrix you want to find an inverse for is 0, then that means that A is singular, which then means also that A inverse does not exist.